Hi, professors. Ladies and gentlemen, good morning. I am Sito Chen from GT College, and today I'm glad that I have the opportunity to present my research topic, doing indefinite integrals without integration. This is the outline of my presentation. So first of all, I would like to talk about my basic idea and inspirations. Residue theorem is a central tool in complex analysis, and it is widely applied to evaluate some monstrous improper definite integrals, such as this one, which surprisingly has a nice closed form. So it is natural to ask, why don't we apply residue theorem on indefinite integrals? So for the first step, we want to make it improper. We would like to apply residue theorem later, and residue theorem often deals well with improper integrals. So we would like to try to make the integral improper. So we will make the substitution u equal 1 over t minus c, and the first equality is due to the fundamental theorem of calculus, and the second equality is due to the transformation. For the second step, we will use an identity. The identity is, in short, a equation relating a general form of an integral to a sum of two line integrals. I can provide an intuitive proof for this. Along these two paths, the logarithm only differs by 2 pi I. So because under the limits, as delta tends to 0, the two paths are infinitely close to each other. And because they are in opposite directions, so the identical parts will cancel, and leaving the 2 pi I factor behind. And we would like to apply this identity to the improper integral that we obtained in step 1. And after some simple math, we can obtain a relation between the indefinite integral and the sum of two line integrals. For the first step, we want to make the contour closed, because residue theorem is only applicable to closed contours. On one end, we will attach a infinitesimally small circle, and on the other end, we will attach an infinitely large circle. And finally, unfortunately, the integrals over these two extra pieces of contours tend to 0. And finally, we can obtain a relation between an indefinite integral and a contour integral. And for the fourth step, which is the most exciting one, is to apply the residue theorem. It is easy to see that the contour integral is equal to 2 pi I multiplied by the sum of residues. So we finally obtain an equation that relates the original indefinite integral to the sum of residues. And with a variation of notations, we can obtain this equation, which is more rigorous than the one in the previous page. And we will call this equation star. I would like to talk about the advantage of this formula. First of all, the computation of residues does not require any knowledge of integration. So therefore, indefinite integrals can be solved without doing integration at all. For poles, only differentiation and computation of limit is required, and for essential singularities, only series manipulation is needed. There's also another advantage that this formula is especially useful when finding the antiderivative of rational functions. Here's a challenge. We want to find the antiderivative of this crazy function. And if we attack it with the usual method, which is the partial fraction decomposition, it's going to be quite tedious and time-consuming as well. So we would like to make use of this formula that we derived. Firstly, we'll take c equals 0, and also we will make use of this simple, well-known identity for simple poles. Because the residues here is easy to compute, so we can obtain the long expression here in less than a minute if you are familiar with this formula. And this is much simpler than partial fraction decomposition. Next, I would also like to talk about the constraints. The above simple analysis does not really apply to functions with infinitely many poles or singularities, such as cosecant or secant. This is because the reciprocal substitution in step 1 will lead to a cluster singularities. For example, cosecant t has poles as integer multiples of pi, and if we apply the transformation, we will obtain a pole cluster near 0. So, but still, we would like to see what will happen if we blindly apply the standard procedures to cosecant. Then after going over the standard procedures, we obtain this contour integral, which has this secant 1 over z here, which is quite problematic because it has non-isolated singularity at 0. So residual theorem cannot be applied, and the star equation can't be applied as well. So some other techniques are needed. We will want to overcome the constraints. So we find out that if we apply some small tricks, the star equation can be applied as well, and the formula can be generalized to the case of infinitely many singularities. The tricks are slightly modifying the contour and adopting some other minor techniques. But this small step needs a relatively long process. Firstly, we modify the contour. Suppose Fz only has one singularity cluster at C, and let Bn to be a sequence of circular contours centered at C such that the Bn can avoid all the singularities of F, and it shrinks to 0 as n tends to infinity. Sorry. So we would like to modify the contour like this. We will subtract a Bn here and add a Bn after that, and also take the limit n to infinity. And in essence, we are doing this modification on the contour. On the right-hand side, the first integral can be evaluated using the star equation, because for every n, only a finite number of poles or singularities is enclosed in the contour. And for the second integral, we need other techniques. The other technique is not really surprising, but only making use of asymptotic relation. The basic idea is that if we can find a simple d function that is asymptotically equal to this integrand for almost all theta, then we can find the question mark to be this integral and can be evaluated in closed form easily. For example, if if gz is secant 1 over z, then we can see that the integrand is indeed vanishing for almost all theta, and thus the whole integral is indeed vanishing as well. So going back to the antiderivative of cosecant, we will start at this contour integral, and if we modify the contour, and then we can see that indeed the second integral is 0 under the limits as n tends to infinity. We can show that the integrand is vanishing, so the integral is vanishing as well. And after some very tedious calculation of residues, we obtain this expression. It is important to note that the first term will become independent of x as k tends to infinity. And for the second term, you can recognize this as the quotient of sine and cosine in their product forms. So we can finally obtain something that we've seen often in textbooks, which is this one. We can also even provide a general formula, which is this one, but it is ugly and difficult to understand. So I think the methodology behind is more useful than the result itself. Moreover, I would like to talk a few words about another advantage of this formula. This formula can actually be used as a very weak tool for analytic continuation. Throughout the derivation of this formula, this crazy formula, we only assume that theta is not equal to c. So I should ideally expect that this expression should converge for all theta, except at theta where it is constrained by the nature of the original f, which the nature of the function is that it really has poles there. You can't remove it. So I think this expression can be called a globally convergent expression of the antiderivative of f. So in some sense, it is a tool for the purpose of analytic continuation. So this is the end of my presentation. Thank you.
Thank you.